All right, welcome back to our fourth video in this new playlist. In this video, we're going to be going over some example applications of Kalman filtering. The examples present three different models. There's the resistor revisited, which is the same model that we looked at in playlist 1, but this time we're going to be looking at it from a Kalman filter perspective. The second system will be a constant velocity motion system. So there will be two states, position and velocity. And we'll look at the damped harmonic oscillator, which is also two states, but it will be more dynamic than the constant velocity motion. Finally, in this video, we're going to take a look at the types of plots that are produced by the simulations. So these are all discrete time systems. They increase gradually in complexity. The first one, the resistor, is a single state static system. State does not change with time. The second one, the constant velocity motion, is a two-state system. One of the states is dynamic, the other one is static. We'll be having position as the dynamic state and velocity as the constant static state. The third model will be the damped harmonic oscillator with two states once again, but this time with both states being dynamic. The MATLAB and Python files can be found out on the GitHub, and here's the URL for the GitHub repository. The MATLAB files are no longer maintained, so they're somewhat older, but you can download those if you have MATLAB. I am currently working primarily with Python, so I would use the Python scripts. Download the scripts and play with them. Modify the initial conditions, the number of samples, play around with the various noise parameters for measurement noise and process noise, and then observe how the plots change. If you want to share your mods to the programs with others, you can upload them to the GitHub repository, but I would request that you put them in the student_contrib folder so as to not clutter up the SRC folder. And I would ask that you add a suffix that identifies who you are and who actually contributed this particular version, and to not overwrite other people's versions when they upload theirs. So just put a suffix that indicates, say, your YouTube ID. All right, now we're going to take a look at the types of plots that we use here with these simulations. The first type is a truth measurement estimation plot, or what we call a TME plot. It's a time series plot of ground truth model, of the measurements and the state estimations. And then the other type of plot is a Kalman Sawtooth plot, which is a specialized plot for assessing the growth and reduction in uncertainty. Here's an example of a TME plot. You'll see that this is from the damped harmonic oscillator, and the first state, which has a measurement model for position, there is a red line there, which represents the measurements. In the plot below, there is no red line because there are no measurements of velocity. The only measurements available in this model are position measurements. Otherwise, in all of the plots, you'll have estimation and truth model. The truth may or may not include the process noise, depending on how you want to set it up. You can also make it, as I do in some of the simulations, so that it has a process noise that has the same statistics as the model, as the Kalman filter model, but has perhaps less variance, or is scaled down. And the Sawtooth plots, they interleave the pre and post update values of the diagonal elements of the P matrix. So they show growth over time in uncertainty in the estimation of a given state, and then they show an immediate reduction in uncertainty after the update is applied. So here's an example. You can see in going from the time step 0 to time step 1, there is a growth in uncertainty, as we talked about in the last video. And then immediately at time step 1, once we have a measurement, we can update the covariance, and therefore there's a rapid drop, immediate drop in the uncertainty. So you get this sawtooth pattern. And typically you'll see there's a initial transient value here where it's maybe large in the beginning, but then it converges to a steady state value where then there's just a steady state increase in uncertainty with the time extrapolation, and then an immediate reduction in uncertainty once you apply the measurement. Okay, that's it for this video. Where are we? We've given you an overview of the 3 graduated examples that we'll be looking at in the next few videos. We've seen examples of the 2 kinds of plots that the simulations produce. And so what's next? Well, next we're going to drill down on the first model, the Kalman resistor model. And then in videos after that, we'll look at the other 2 models. And that's it for today. We'll see you in the next video. Thank you for watching.